we need to learn about this concept called hybridization between the atom. Hybridization is the concept of mixing the atomic orbitals into new hybrid orbitals with different energy and shapes than the component atomic orbitals, which are suitable for pairing of electrons to form chemical bonds based on the valence bond theory. So basically, we learn that the orbitals in the unhybridized atoms will be 2s, round, and for the 2p, it will be dumbbell shape. However, when they hybridize, they will form new shape or new orbitals. And these new shape and orbitals will then bond with other atoms through overlapping or hybridized orbitals with the shared electrons. And these are called covalent bonds. Okay, so for the carbon, it will form 4 bonds with hydrogen and they will overlap with each other to give you the new bonds and shape. In organic compounds, the atoms form covalent bonds, which are formed from the sharing of electrons. For the sharing of electrons, it can be done through overlapping of orbitals. The s and the p's atomic orbitals of carbon, nitrogen, and oxygen are not suitable for overlapping directly with one another. So the chemists come up with a theory that states that the s and p atomic orbitals of these atoms must combine to form hybrid orbitals for overlapping. This combination process is called hybridization. Only the valence orbitals are involved in the hybridization for bonding. Okay, so for hydrogen, because there's only one orbital, there's no hybridization required. For carbon, nitrogen, and oxygen, the 1s orbital is not the valence electrons. Okay, the electrons in the 1s orbitals are not valence electrons, so they are not involved in hybridization. However, the valence orbitals, the 2s and the 2p orbitals, they are involved in hybridization. So there are 3 types of hybridization which we will learn. They are called the sp3 hybridization, sp2 hybridization, and sp hybridization. Let us look at the video that can help us to understand more about hybridization.
Howdy y'all, Mr. Cosby coming to you from beautiful Atascocita, Texas with another chemistry lesson, and today we're going to talk about the hybridization of atomic orbitals and the valence bond theory. In this lesson, the valence bond theory, the hybridization, the hybrid orbitals, and much, much more. You'll need your periodic table, and you need to be familiar with the Vesper theory, molecular shapes, Lewis dot symbols, the orbital shapes, and electron configuration. And if you're not sure of any of these areas, you need to go to my YouTube channel, find the lesson, and check it out, because it's a must to know these items. Alright, if you remember, the Vesper theory told us that the shape of a molecule was determined by the repulsion of the bonds and the electron pairs, or the electron regions, and it would be most stable when these regions were as far apart as possible. And this worked fairly well, but it couldn't explain why boron had 3 equal bonds, or why carbon had 4 equal bonds, or even why phosphorus could form 5 equal bonds, or the fact that it could do 5 bonds when we know it's supposed to be 3. But with quantum mechanics, we were able to introduce the valence bond theory. And the valence bond theory described how the molecular shapes and molecular orbitals are formed by the hybridization of the atomic orbitals. And this was used to explain how atoms can have bonds of equal energy even though the electrons are in orbitals with different energies, such as s, p, or d orbitals. So let's look at carbon. Carbon is a 1s2, 2s2, 2p2 electron configuration. It has 4 valence electrons, and its Lewis dot symbol looks something like this. We have a 1s orbital and 3p orbitals. But when it bonds, we end up with 4 equal bonds. How? Well, hybridization is the answer to that question. Hybridization is the mixing of an unequal or a set of unequal orbitals to obtain a new set of equal orbitals. And this new set has properties somewhere between the original unequal orbital. Let's understand orbital hybridization. The first part is hybridization occurs on the central atom. So if we look at something like methane, carbon is the central atom, and that's where we expect hybridization to occur. Secondly, the number of new hybrid orbitals always equals the number of orbitals used. We can have one s orbital and one p orbital, and that will give us 2 sp orbitals, 2 brand new orbitals. Or how about 1 s orbital, 3 p orbitals, and 1 d orbital? That would give us 5 sp3d orbitals, or 5 new orbitals. Part 3, the new orbital's name will consist of the number and kind of orbitals hybridized. So if you have an s and a p, you're going to have 2 sps, or an s with 3 p's and 1 d. Count them up and it will give us 5 sp3ds. Would be a new name, and the 3 would be telling us how many p orbitals are. And then our fourth part here, both the energy and the shape are changed in the new orbitals. So a 1s plus a 1p, of course, will give us this new shape for the 2sp, somewhere in between the 2 originals. Hybrid orbital shapes. If we have an s plus a p, we get 2sp, and that's going to look something like this, and that's linear. Now if we have an s and 2 p's, that's going to give us 3 sp2s, and that's going to look like this, and that's trigonal planar. Now an s and 3 p's will give us 4 sp3s, and I think you can already figure out that that's tetrahedral. Now we have an s, 3 p's, and a d. They're going to combine and give us 5 sp3ds, and it's going to look something like this, and of course that's trigonal bipyramidal. Now we have an s plus 3 p's plus 2 d's. Add them up, we get 6 brand new sp3 d2s, which would look something like this and is considered octahedral. Just a little bit of review there. The SPs are going to be linear. The sp2s are going to be trigonal planar. The sp3s are going to be tetrahedral. The sp3d is going to give us a trigonal bipyramidal, and the sp3d or the sp3d2s are octahedral. Now remember, hybridization doesn't always occur, such as on hydrogen, fluorine, and chlorine. They only have one bond and really don't need to hybridize. So let's look at some examples of hybridization. Beryllium has an electron configuration and 2 outer shell electrons, but we know that it makes 2 equal bonds. So what happens here is, even though this is our Lewis dot symbol, when it bonds we get these 2 separate bonds and they're equal. Therefore, there must be some hybridization, and so one of the s's jump up into the p's, and then they combine to give us 2 brand new sp2 or sps, and it's a linear molecule. Let's look at another example. Carbon. And we see that it has 4 valence electrons, 2 in the s and 2 in the p's. But we know that even though this is the Lewis dot symbol, when it bonds, we get something that looks like this. Therefore, one of the s's jumps up into the empty p, and these all combine to give us a brand new set of sp3s. And of course, that's a tetrahedral molecule. And this is how phosphorus would occur. I'm going to use the shorthand here. And we see that it has 5 valence electrons, but would only produce 3 bonds. So the Lewis dot symbol, 3 bonds, not 5. So how could it possibly make 5 bonds? Well, we borrow from the 3Ds. One of the S's jumps up there, and now we have 5 orbitals to make 5 bonds. So 1s and 3p and 1d will give us 5 brand new sp3ds. And it should look something like this. And that's trigonal bipyramidal. All right, let's recap. The Vesper theory can't do it all, so we came up with the valence bond theory, which introduced the idea of hybridization and hybrid orbitals. And that gives us our shapes, or helps explain the shapes with the Vesper model as well. If you have any questions, send an email to Mr. Kazi at mrkazi.com, and be sure to subscribe to my...
Okay, so for the 3D orbitals diagram, this drawing shows the 3D orbital shapes of the orbitals. It shows the boundary verified by experiment between which an electron moves as defined by its level of energy. During hybridization, the orbitals will undergo 3 stages. So what are the 3 stages? The orbitals will undergo changes from the first state, which is the ground state, and the next one, which is the excited state, and followed by the hybridized state. So for the ground state, the electrons, for example, in the 2s orbitals, move constantly between a spherical boundary. There are 3 identical dumbbell-shaped p orbitals, 2px, 2py, and 2pz, pointing in 3 directions, the x and the y and the z respectively. The electrons in these orbitals move in either side of the orbital except the central knot. In addition, if the orbitals is occupied with 2 electrons, not necessary that both must stay together. Each can occupy any side of the orbitals. Okay, that means the orbitals can be here, okay, or they can be here, or they can be here. They do not need to be together at the same side. For excited state, it involves the promotion of electrons to the next level of energy. Therefore, there is no change in the shape of orbitals in this state. For hybridized state, it means that both the 2s and 2p orbitals, they merge together to form a hybridized or new orbital shape. For example, the sp3, sp2, sp hybridized atoms. Okay, first we'll learn about the sp3 hybridization. During hybridization, the orbital shape change. Hybridizing the 2s orbitals with the 3 2p orbitals will form 4 sp3 hybrid orbitals. Okay, look at here. We have a 1 2s orbitals and 3 2p orbitals. When they mix together or they go through hybridization, they will form a total of 4. 1, 2, 3, 4. sp3 hybridized orbitals, or sp3 hybrid orbitals. Okay, so look at here. At the initial state, you have 1 orbital, 2 orbital, 3 orbital, 4 orbital. After hybridization, the orbitals do not disappear. They form a new shape, and you have a total of 4 of them. 1, 2, 3, 4. And what is the name of the new orbitals? Okay, because there's 1 s orbital being evolved and 3 of the p orbitals mixed together, we call it the sp3 orbitals. For the sp3 orbitals, we use carbon example. For the electronic configuration of carbon is 1s2, 2s2, 2p2 at the ground state. So for the orbitals diagram, we do not need to actually draw the 1s orbitals. Okay, we just need to draw the 2s and the 2p orbitals. So we will only draw the 4 electrons here, which is the 2s2, 2p2 orbitals. When the electrons get excited, one of them actually becomes higher in energy and they goes to the 2p orbitals. Okay, it becomes higher energy and goes to the 2p orbitals. And these 2s orbitals will mix with the 3 2p orbitals to form 4 sp3 orbitals, each with 1 electron. And we call this the sp3 orbitals. So the sp3 hybridized carbon will have 4 unpaired electrons for sharing with other atoms to form 4 bonds. And the sp3 orbitals, they are arranged in tetrahedral shape. Okay, they do not like form a flat cross. Okay, they form a tetrahedral shape, and the bond angle is 109 or 109.5 degree. And next, we take a look of the sp3 hybridization in nitrogen atom. The electronic configuration of nitrogen is 1s2, 2s2, 2p3 at the ground state, 1s2, 2p3 at the ground state. During the excitation or the excited state, one of the electrons get excited and it becomes higher in energy. So you get these white electrons that's promoted from the 2s to the 2p orbitals, and these 2s orbitals will mix with the 3 2p orbitals to give sp3 orbitals, in which we have 2 electrons in one of the orbital box and the other 3 singly here. The 3 2s3 orbitals, they have 1 electron each, and 1 sp3 orbitals have 2 electrons, which is a lone pair. Okay, we also call this a lone pair. The sp3 hybridized nitrogen has 3 unpaired electrons for sharing with other atoms to form 3 bonds. The lone pair is not for bonding, so nitrogen will form 3 electrons. The 4 sp3 orbitals, they are arranged in trigonal pyramidal shape, and the bond angle is 107 degrees. Okay, because this is a lone pair, so you can view the top of this nitrogen as like empty, so it forms like a pyramidal shape, okay, or a trigonal pyramidal shape. Bond angle is 107 degrees. Next, we have sp3 hybridization in oxygen atom. The electronic configuration of oxygen at the ground state is 1s2, 2s2, 2p4. Okay, so for the valence electrons, it will be 2s2 and 2p4 over here. And during the excitation state, one of the electrons get excited, okay, and you will be promoted up to the 2p orbitals. So you will get 2 lone pairs in the 2p orbitals and 1 in one of the 2p orbitals. And these 4 orbitals will undergo mixing or hybridization to form 4 sp3 orbitals. So you have the lone pairs and then the 2 electrons. The 2 sp3 orbitals, they have 1 electron each, and 2 sp3 have a lone pair each. Thus, the sp3 hybridized oxygen has 2 unpaired electrons for sharing with other atoms to form 2 bonds. These lone pairs are not for bonding. Okay, so you have lone pairs and then you have 2 electrons in your sp3 orbitals. And what kind of shape is it? It will be a bent shape. It's like a V shape. Okay, as seen from here, it's like a V shape. And the bond angle is 105 degrees.